Hello everyone, welcome to QST seminar. Today we have Venkatesa Chandrasekaran from IAS and he'll talk about large N algebras and generalized entropy. Over to you, Venkat.
Thank you so much for the invitation. So I'll be telling you about work that I did with Edward Witten and Jeff Pennington on ADS black holes and their generalized entropy. And if I have time, hopefully, I can tell you about some related work that was also with Roberto Longo on an analogous story for deSitter space. The overarching motivation here is to get a better understanding of what the generalized entropy is from a Lorentzian perspective. But just to explain that motivation in a bit more detail, because I feel like the setup is really the most important part in this particular story. So we all love the generalized entropy. It's important in black hole thermodynamics. It's also important in holography because it tells us a lot about the bulk boundary dictionary. But it's a bit of a weird object, at least in the way that we normally use it, particularly in the context of black hole thermodynamics, because we have, on the one hand, the von Neumann entropy of matter fields that are outside the black hole. On the other hand, the other term here, the area term, is at worst just some geometric term that we're adding in by hand, a geometric area of the black hole. And at best, it's some coarse-grained entropy associated to counting microstates of some UV degrees of freedom that maybe we don't fully understand yet. But on the face of it, at least in semi-classical gravity, these two things are on a pretty different footing. And it would be nice if we could give some semi-classical understanding of generalized entropy, where the area term and the matter term are not treated in fundamentally different ways. So when I say, can we get a more microscopic understanding of it, what I really mean, I don't mean like a full, microstate counting or anything ambitious like that. I just mean whether there's a more effective field theory picture for where the generalized entropy really comes from. Is there some Hilbert space with some density matrix, and there's some trace rho log rho that we can compute, for which both the area and the von Neumann entropy get spit out all at once instead of having to put these in by hand. And so just from the start, I want to anchor down the exact setup that I'll be considering for most of the talk, just so you have this picture in mind. So imagine we have a two-sided eternal black hole, and then we perturb that black hole by some energy that's order 1 in terms of G Newton counting. Then from the semi-classical Einstein equations, we get a metric perturbation, which is going to be order G Newton, and the resulting geometry will look something like this, where we have two horizons, and we have an apparent horizon that goes from one to the other. But okay, so this is the most accurate picture. But since we're only going to be working to linear order in the metric perturbation, we can use a simplified picture that just makes the analysis a lot easier, which comes from the fact that at linear order, we can always do a gauge fixing of the new horizon so that it coincides with the original horizon before we did the perturbation, so that we can just do everything on top of the original eternal black hole geometry. And whatever perturbations we add, we just treat them as some stuff that's falling into that's falling on top of the old event horizon. And in particular, any geometric change to the black hole is now treated as itself some field that's propagating on top of the black hole. Like, for example, if the expansion of the event horizon is now some non-zero quantity, that's just some field that propagates on top. Okay, so for this kind of setup, I want to ask the following question. Is there some algebra of operators in quantum field theory coupled to gravity, where I'm really treating gravity dynamically. It's not just quantum field theory on some curved space-time. Gravity is really dynamical. So in that setup, is there some algebra of operators, for example, maybe associated to the causal wedge here, such that if you give me some configuration of matter fields on this geometry, there's some associated state whose generalized entropy, whose von Neumann entropy is the generalized entropy of this perturbed black hole. And I'm specifically using algebra of operators here as opposed to Hilbert space for reasons that will be clearer later. I'll be able to give you an answer to this question in a definitive way for an algebra of operators, but I won't be able to give you a Hilbert space. But the reason for that will become apparent. So this is a question that's been asked before, for example, by Donnelly and Friedel, Jennifer Lin, Jaffers, and Kolchmeyer. And in these scenarios, it's usually brought up in the Hilbert space picture, and oftentimes ends up requiring maybe one or more ad hoc elements that are strewn in. And my goal here is to maybe convince you that this algebraic formalism is a more clean and more generalizable approach to this question. Okay, so the first thing you might ask is why do we even want to do this? Like, who cares? Especially if you're used to doing Euclidean quantum gravity, we can already derive the generalized entropy from something like the Lefkowitz-Maldacena calculation in ADS-CFT, and which, you can kind of generalize beyond. It's not really too specific to ADS-CFT. It's really like Gibbons. It's a version of the Gibbons-Hawking calculation from a while ago. So why do we need some other way of deriving it? And part of the reason is something I mentioned earlier, which is it gives us, in some sense, a bit more of a microscopic interpretation of generalized entropy. And by microscopic, I like to use the phrase hydrodynamic, because what I really mean is we have our matter degrees of freedom, and we're looking for some sort of collective mode of quantum gravity. So we don't know about the full UV degrees of freedom, but the UV degrees of freedom trickle down to some collective mode in the semi-classical effective field theory quantum gravity. And that collective mode combined with the matter degrees of freedom are going to give us the area term plus the matter entropy. So that's the goal. And
sorry, Ivan, can I ask you? You said something like this, but I'm not sure. Is your definition in terms of algebras going to be to first order in G Newton or H bar, or what precisely? Or is it an example? Yeah.
It's not. It's perturbative in G Newton.
G Newton.
Yeah, okay. Yeah. It's definitely, it's absolutely perturbative in G Newton. Yeah. And in a sense, it's first order in G Newton.
First order. Okay. Yeah. Thank you.
Yeah.
Can I ask a question?
Mm-hmm. Of course.
Yeah. So you use the word collective coordinates in the same sense that hydrodynamics emerges in fluid gravity, coming from collective coordinates of, let's say, a black hole geometry.
Yeah.
It's in that sense. Is that right? I mean, they're like.
I don't know if I can give a very precise answer to that question, but maybe it'll become clearer later. It is a collective coordinate.
Yeah, so
that will end up being the relevant mode for the area term. Yeah.
Yeah, I mean, like in fluid gravity, there are the 4 zero modes. For the black hole, one is the radius, and the other are the 3 boost parameters which you could use in order to 3 or 4 depending on your dimension. And then those are the things that you promote to functions, slowly varying functions of in space time, and then translated to, you have something like that in mind, and you
absolutely exactly yes. This hydrodynamic mode that I'm mentioning will end up being it'll be a quantization of the boost mode associated to the black hole.
Okay. Thank you.
Yeah, of course. Okay. So just one last point of motivation, which perhaps is maybe the most interesting one. So this Gibbons-Hawking derivation that we're all used to, that spits out the generalized entropy or the Ryu-Takanagi formula, however you want to call it, uses this mysterious boundary condition where if you, so the way you might like naively try to tackle the question of what is the entropy if you were coming at it from Euclidean gravity is you would start in the bulk of your manifold. You would slice up, your manifold into Cauchy slices. You would pick some Cauchy slice and you want to compute the trace of something. So you would compactify the time direction and see what happens. And if you do that, you get something like a cylinder. And as Gibbons and Hawking observed a long time ago, that would give you the wrong answer for the entropy of the black hole. Instead, what you have to do is just fix boundary conditions at infinity and then fill in any smooth bulk saddle that where the thermal circle contracts to zero size and then find the dominant one. So the problem with that is, while that gives you the right answer, it's not really clear from a more fundamental perspective, at least in semi-classical gravity, why this thermal circle shrinking to zero size is the right thing to do, other than the fact that it gives you the right answer. And so that itself is not really an issue, but the real issue is you can't really interpret that quantity anymore as an actual trace of some quantity. So the thing you set out to calculate at the level of definition is not really the thing you end up with. You could, I mean, usually we interpret it as a boundary entropy in the context of ADS-CFT, but if you forget about ADS-CFT, or you want some bulk notion of an entropy in gravity, then this approach isn't exactly the one that you might want to take. So a direct Lorentzian approach is one that is what we're going for here in this talk. Okay. And are there any other questions so far? Because now I'm going to get into the more like detailed things.
I mean, I was going to say, just as a comment, not important, that, I mean, even aside from ADS, the best you could hope to do, I suppose, is try to define a Hilbert space vis-a-vis asymptotic boundary conditions. It's asymptotic data.
Right.
Even in asymptotically flat space, right?
Okay,
and from that point of view, I think it's perfectly fair to say I'll just impose the boundary conditions at asymptotic infinity to be a circle, and then allow the geometry to do whatever it does in the interior, right? And interpret it as a trace as far as the Hilbert space is concerned. Which one is different? Okay, but anyway.
I don't think there's anything wrong with that, but it's a bit, so you would have to be resigned to be interpreting it, I think, as it's some sort of a boundary trace in some putative boundary theory away from ADS-CFT. Like, you can't really think of it as a trace of some bulk state on some slice, which, I mean, there's nothing necessarily wrong with that, but if we can give a bulk interpretation as some trace, then that would be great, because then at least it would look more like what we think of the entropy of some quantum field theory. Yeah.
Thank you.
But I completely agree with you, because whatever I'm doing here is really a semi-classical effective picture. So ultimately, in quantum gravity, in full quantum gravity, I mean, I think like only the boundary entropy is going to make sense anyways. Yeah.
Thank you.
Yeah, for sure. Okay, so in order to try and answer this question, I'm going to use some methodology from algebraic quantum field theory, following this paper from last year by Edward, which itself was motivated and based on an earlier paper by Hong Liu and Sam Leuthauser. And there are also some other related works that are in the same sphere of questions. There's one by Papadorimas and collaborators from back in 2016. And I'm going to use ADS-CFT to put things on a more solid footing, just to make the details of the bulk and boundary aspects very precise, but you could very readily just take everything I say and forget about ADS-CFT itself and just talk about it directly from the perspective of semiclassical gravity, and everything will go through. So that's one reason why this particular formalism is nice. It might help you understand these questions in more general context, in particular, for example, like we did with deSitter. Okay.
Talking about the bulk, are you going to assume something, some quantum gravity correction at the singularity or something? I mean, how are you going to treat the singularity?
No. Yeah. So for this talk, the only thing I'm doing is I'm taking Einstein gravity and coupled to matter, and I'm going to consider linearized perturbations on top of on top of the like classical sector. And I'm also going to include some additional modes that will become clear, which come from quantizing conserved charges in associated to the black hole in Einstein gravity. So I'm not doing anything beyond that. So it's just solving the semiclassical Einstein equations and quantizing the linearized perturbations on top.
So you are going to work at the level of the horizon, right? I mean, you're not going inside.
Yeah. I'm not going to touch anything associated to singularity. That's right. This is all about like the thermodynamics associated to the black hole. Okay. So I'm just going to very briefly, well, not very briefly, but attempt to briefly review some aspects of this earlier paper by Edward, which uses these algebraic QFT techniques to massage ADS-CFT into an algebraic form. So to be very concrete, let's say we consider n equals 4 super Yang-Mills on the boundary, and we restrict our attention, as we often do, to the single trace operators in the theory. In particular, I'm going to consider trace subtracted single trace operators, which have connected correlation functions that go like 1 over n to the k minus 2 for the connected part of a k-point correlation function. And also I'm going to be converting back and forth between n and g Newton eventually. So just to remind you that g Newton, goes like 1 over n squared. So at n equals infinity, these single trace operators, only the 2-point function is going to survive, and everything will just become products of 2-point functions. So in the n goes to infinity limit, you just end up with the generalized free field theory. So if we focus on this generalized free field theory, I'm going to consider the algebra of these single trace operators. In particular, I want to consider the algebra of the non-central single trace operators, meaning each of the operators in this algebra has some non-trivial commutator with other elements of the algebra. So let's focus on this particular algebra. And if we go back to the setup I mentioned earlier with the two-sided black hole, we know that in the large n limit, the two-sided black hole is dual to the thermofield double state associated to the 2 copies of the boundary CFTs. This was, due to Maldacena from a long time ago. So we have a pair of these single trace operator algebras associated to each boundary. And so I'll just label those AR naught and AL naught, where the comma 0 notation will become evident later why I'm attaching this extra label to it. So we have the single trace operator algebra for the right and the single trace operator algebra for the left. Now, an important question is, what is the role of the Hamiltonian in this algebra? And the form so let's say we focus on the right Hamiltonian. Whatever I say about the right will analogously go through for the left. So the form of the Hamiltonian is roughly speaking something like this, which in particular, it's some integral of some operator like trace f squared, but it has this extra factor of n up front. So if you compute fluctuations in the energy of the trace subtracted Hamiltonian, that thing is going to scale like n squared. So when you take the n goes to infinity limit, the Hamiltonian has unbounded fluctuations, which means that at n equals infinity, this operator here is not going to be in this single trace algebra because of these fluctuations.
So, sorry, when just once, when you say there's an n in front, the Lagrange, this is with f square normalized so that its 2-point function is
order 1, yeah.
Order 1.
Exactly, yeah.
Okay. Thanks. Okay. Thanks.
Yeah. Okay, so this fact that the Hamiltonian has this like n scaling as n goes to infinity is essentially the reason for the following claim that these single trace algebras, AR naught and AL naught. So the claim is that these two algebras are what are called type 3 1 algebras. The one here is not too important. You can forget about that. The main thing is they're so-called type 3 algebras. Okay, so what is a type 3 algebra? A type 3 algebra is at a technical level, one in which the modular Hamiltonian of the state that you use to generate the algebra, that modular Hamiltonian has a continuous spectrum. So that's a technical definition, but for us, we don't need something that technical. All we really need is the fact that the one-sided Hamiltonian of this two-sided system, this thermal field double state, so the one-sided Hamiltonian has a continuous spectrum. Why does it have a continuous spectrum? Well, the energy of so we're starting with the black hole and we're basically considering perturbations on top of the black hole, right? So our Hilbert space is going to be constructed from these linearized perturbations on top of the eternal black hole. The energy of the black hole goes like n squared, but perturbations on top will be order 1. So when the n goes to infinity limit, the gap will go to 0 and you'll get a continuous spectrum for this one-sided Hamiltonian, which is the telltale sign of a type 3 1 algebra. And the type 3 1 algebras show up all the time in quantum field theory, in ordinary continuum quantum field theory. And here they're showing up as an artifact of the large n limit. And the reason type 3 1 algebras are relevant is they're algebras in which there is no well-defined notion of a trace. If you try to compute the trace for any operator in the algebra, it's just going to blow up. Because there's no well-defined notion of a trace, there's no way to define density matrices. If there's no way to define density matrices, you cannot compute entropies, and so on. And this is the standard situation in ordinary quantum field theory.
I have a question.
Yeah.
So you already have a quantum field theory in n equals 4 super angles, right?
Yeah.
I mean,
yeah.
So I mean, I don't see why you have to invoke the large n limit.
But because so what I'm saying is, so at finite n, sorry, I should have clarified. When I say quantum field theory is a type 3, ends up giving you a type 3 1 algebra, what I specifically mean is the following. If you take quantum field theory and you split it up into subregions, if you take, for example, some half space on the line in quantum field theory, the algebra associated to that half space gives you something that's type 3. Not about the full quantum field theory itself, but some subregion in the quantum field theory will give you a type 3 algebra. Here, what I'm doing is I'm not considering subregions. I'm considering the entire CFT as its own theory compared to the other CFT. So I have two CFTs, and my subsystem here is one of those CFTs, which at finite n is just gonna be type 1. It's not going to have any type 3 problems. But in the n goes to infinity limit, despite the fact that I'm not considering subregions, you still get something that looks like it's type 3.
Why is the CFT going to be type 1? Because it will always have a continuous spectrum, right? I mean,
it has, I mean, there's infinitely many eigenvalues, but there's a gap. It's not like there's a gap between all the different excited states. It's discrete. It's a discrete spectrum at finite n.
Well, okay.
Yeah. One question. What role did the absence of Hamiltonian play for this argument?
It's sort of maybe I didn't phrase it properly, but it's not that the fact that the Hamiltonian is not in the algebra is directly the reason for this. It's that both of those things are coming from the same issue, which is this fact that as n goes to infinity, the energy is the energy of the black hole is blowing up.
But you can find states. Okay, you're saying, but you can find states which have finite energy, right? So I don't quite understand what is this measure of fact that.
What do you mean that you can find states which have a finite energy? Energy differences for sure, but.
No, I mean, what does it mean that the expectation value of h minus 1 point function?
Sorry, no. Sorry. The trace subtracted energy will definitely be zero, but by construction. When I say the energy blows up, I just mean the expectation value of the Hamiltonian itself. So the energy blows up and fluctuate, and the fluctuations of the energy in the thermal field double state also blow up.
But are we talking about a particular state, or this is you're making?
Yeah. I'm specifically talking about building up a Hilbert space from the thermal field double state. So my base starting point is the thermal field double state, or the eternal black hole in the bulk, and I'm considering excitations on top of that. If you, for example, were to consider vacuum ADS,
yes,
instead, then the energy is just zero.
Yes.
And up to some constant, and excitations on top of that also have some order 1 energy. And in that case, you're not going to get this emergent. I mean, it's not going to have this. If you just consider the full theory, the full boundary theory, you're not going to get some type 3 thing.
I see. Okay, thank you.
Yeah.
Can I ask a question?
So, assuming that it has an infrared cutoff or something, because only then will it give rise to a finite spectrum, or else if you consider the entire space, if you consider the entire R4 or R3, then I don't think you'll get a discrete spectrum for any field theory, right?
I'm not sure that part is relevant here. It's just the energy spectrum can be discrete. You're worried about like having some infinitely many soft modes or something, or?
Yeah, I mean, if you have an infinite space, if you have R4 or say R3, then for instance, the momentum modes are infinitesimally close to each other, right?
Yeah.
I mean, unless there's some cutoff, there's some infrared cutoff, you are in a box or something, then I don't see how you could have a discrete spectrum.
I think he was talking about the CFT, if I may.
Yeah, CFT. I'm talking about the CFT. Yeah.
Usually one quantizes on the sphere.
On the sphere, yeah.
Yeah, on the sphere. Yeah. So if you're talking about the sphere, then it's okay. I guess.
Each boundary is a sphere for him. Yeah. When sorry to slow you down.
No worries.
Please don't mind, because it will help me understand the physics a little. If I can go back to the Rindler example for just a regular quantum field theory. Now, now just to understand the analogy there, the Rindler Hamiltonian, say in the Minkowski vacuum, does have a infinite energy in a sense, expectation value.
Yeah.
And also the spectrum is continuous there physically because you have these modes deep inside near the Rindler horizon, right?
Exactly. Yeah.
Which can carry sort of no energy or continuously varying energy.
Yeah, exactly.
And is that a kind of good picture to keep in mind in the thermophile double case that, or maybe you're even drawing it here, that you have something like a Rindler wedge in the bulk. You start with your right Hamiltonian and you can deform it all the way up till the right patch, the right horizon. So in a sense, it's sort of a similar story, is it? Or you say that?
That's no, you read my mind. Yeah, that's exactly the picture that you should have in mind. And in fact, what I was going to say is another way to interpret the statement that I made that you have a type 3 algebra for the right CFT in this large n limit is in the large n limit, we expect that the algebra of single trace operators to be dual to the right causal wedge of the black hole.
Yeah.
And the black hole, for the eternal black hole, the structure is, at least for the exterior, is pretty much the same as for Rindler. And so you really do have the same kind of picture where in fact, I drew it here. The boundary Hamiltonian, as we know, can be deformed to the boost Hamiltonian in the right wedge.
Mm-hmm.
And the boost operator, the one-sided boost operator, if it existed, has a continuous spectrum and leads to all these kinds of divergences. And in one particular divergence, that's the one that's really mapped, that's dual to this fact that I said about the Hamiltonian not existing in the boundary algebra, is the fact that the boost generator, so what it does, the one-sided boost generator, and I'm emphasizing one-sided as opposed to two-sided, the one-sided boost generator takes a slice like this, and it maps it to a slice like this. So in the bulk, it kinks your state. I mean, you could think of it as kinking your slice or kinking your state, whichever one, but one of these will get kinked. And when it gets kinked, it dephases the UV modes that are right by the horizon, and that gives you infinite energy.
Yeah.
And so this is not a good operator on the bulk quantum field theory. So that's the bulk version of the words that I said on the boundary. If you wanted to be very fanciful with the words, what you might say is that this is a way to see that in the large n limit of the thermofield double, something like a horizon structure emerges. If you didn't know about ADS CFT at all, and you saw that there was this type 3 algebra emerging from something that was type 1, you might guess that something like some structure like a horizon is emerging within this algebra. But that's sort of a more like fancy way of putting it.
Okay, thank you.
Yeah. Okay. Okay, so everything I've been talking about so far is at the strict n equals infinity limit. But if we want to talk about things like generalized entropy, and we want to think about coupling between matter and gravity, we don't want to work literally at n equals infinity. We want to include some 1/n corrections. And the naive way you might try to do that is to literally just do a power series in 1/n squared, which is what Edward tried to do in his, or that's what he did rather in his original paper on this from last year. But for the purposes of computing things like traces and entropy, that's not the best approach, because it makes it very hard to define quantities that are important, like the trace. The trace goes like e to the n, and if we want to do a power series in 1/n squared, this is not going to be something that has a well-defined power series. And there are various other quantities that we want to compute, which doing a power series in 1/n squared just makes it really hard to get any handle on what happens in this algebraic QFT formalism. So instead of taking that direct power series approach, which is what would happen in this in the way that I've set things up so far, I'm going to slightly take a different approach. So instead of considering the thermofield double in the way that we have so far, I'm going to consider a microcanonical thermal field double in order to, and it'll become clear why, in order to get around this issue of having to do a expansion in 1 over n. So the microcanonical thermal field double is defined very similarly to the thermal field double. The normal thermal field double is just this factor here, and then my energy eigenstates for the left and the right CFTs. But now what I'm going to do is stick in this window function, where this window function is sharply peaked around the classical value E0 of the black hole. For an explicit example and the simplest possible window function, you could just take it to be a Gaussian with some standard deviation sigma. This was considered by Merrill, for example, in order to construct black holes in the microcanonical ensemble. And as I mentioned earlier, the energy of the black hole goes like n squared. If we take the standard deviation to be order 1, and we do a saddle point approximation, then we find that the relevant states are states in which the energy of the state differs from the energy of the black hole by some order 1 number. So sorry, not the relevant states, the fluctuations. The fluctuations in the energy will be order 1 by taking the standard deviation to be order 1.
Sorry, can I?
Yeah.
So normally in a construction of the microcanonical ensemble, you have that delta function thing there. But you don't have the exponential. I mean, then you say that, well, that E0 gets related to beta by an ensemble influence. So you seem to be sort of doing it double.
Sorry, I was just being sloppy with the way I wrote this. There should be like an e to the s factor here that gets rid of this exponential.
I wouldn't write the exponential. I would rather exactly. I would write the normalization term.
There should be a normalization that exactly that gets rid of that. Here I will. Is that you're right. It shouldn't be there. That's absolutely right. And that's definitely what's happening.
Okay.
Yeah. Okay, so the fluctuations in the energy, so just to compare, for the microcanonical ensemble, the fluctuations in the energy are going to be order 1, whereas in the canonical ensemble that we considered earlier, they were order n squared. So what that means is in the microcanonical ensemble, I can just take the n goes to infinity limit, and this operator here, the Hamiltonian subtracted by the energy of the black hole, will be well defined at n equals infinity. I mean, I only talked about the fluctuations. You can compute all the moments and you can convince yourself that it's completely fine because of the fact that the standard deviation is some order 1 number. So because the Hamiltonian, this subtracted Hamiltonian, is perfectly well defined at n equals infinity, we don't need to do a power series in 1 over n squared. We can just directly do everything at n equals infinity. In order to get a bit more insight into what the picture is that we're going to be expanding upon, I'm going to talk about things from the bulk perspective. So in the bulk perspective, so in the n goes to infinity limit, this microcanonical thermal field double is also going to be dual to it's essentially the same black hole as before. The only difference now are the fluctuations in the energy. So you can have the exact same picture in mind that I drew earlier. Just remember that the energy fluctuations are going to be slightly different, and that'll be relevant later. But for this black hole, I'm going to, just for notational simplicity, I'm not going to keep writing this like tilde thermofield double. I'm just going to call it psi. So wherever you see a psi always represents the microcanonical thermofield double state. So for the microcanonical TFD, we can define something called the bulk or the total modular operator. So the total modular operator, for our purposes right now, is just
Sorry, Ven, please excuse me for interrupting.
No, of course, no problem at all.
Okay, but now I'm really confused because as you emphasized, the fact that we were getting those fluctuations was a signal of having a nice smooth horizon in the bulk. Does that mean that the TFT tilde, is some firewall-like state that you've created?
No. Yeah. So the algebra I talked about earlier, the single trace algebra, it's still, so if you forget about the Hamiltonian, so if you forget about including the Hamiltonian or not, if you just consider that algebra by itself, so that's still going to be type 3-1 because the argument for why the spectrum of the Hamiltonian is continuous is still valid because the energy still goes like n squared, but the excited states have order 1 energy, so the difference is still going to go to 0. Excited states on top of the thermal field double. So it's still going to have a continuous spectrum. The fact that the energy fluctuations in the thermal field double are now finite is not going to change that. It's going to change something else, which I will get to, but it's not going to affect the argument that the algebra, the quantum field theory by itself is type 3-1.
Okay. Thank you.
Yeah.
Sorry, maybe.
Wait, can I ask you?
Maybe I did. Sorry, go
ahead. Thank you. I got confused with the microcanonical expressions. Well, in the standard microcanonical ensemble, you take the variable to be the energy instead of temperature. But here it seems that you specified both the energy and the inverse temperature. So what is the variable here?
Oh yeah, here the temperature is really just something that you're extracting from the classical energy of the black hole, but it really is like expressed in terms of energy. I'm considering a energy window around E naught. But I think this was like the point that was made earlier, like that it should be normalized, and this exponential really isn't supposed to be there. I mean, the temperature here is not an actual it's not a statistical temperature. It's just the like fact that if you like have a black hole with some energy, you can like and it has some area, you can pluck out a temperature from that. But I'm really just considering a fixed energy window around this value E naught. So I'm not, it's not a canonical temperature fluctuation or anything like that.
Yeah, I just wanted to figure out what makes the difference between the microcanonical ensemble and the canonical ensemble, that in one case, your, this fluctuations are order n square and the other one is order 1. How does that work? I mean,
so I think the main difference is, in the case of the microcanonical ensemble, since we can tune the size of the window so far as it allows us to still do a saddle point approximation around the classical saddle. Insofar as we can do that, we can tune the window so that the window is small enough so that we don't get arbitrarily large fluctuations in the energy. Whereas in the canonical ensemble, you don't have that freedom. I mean, that's really just the main difference.
Nice.
Yeah.
Okay, thank you.
Yeah.
So it's a microcanonical ensemble that gives rise, that's associated with the type 3-1 algebra, right?
Well, so the fact that it's microcanonical versus canonical doesn't change the fact that these single trace operators in the algebra are type 3-1. That is still valid, because that argument really just, at the end of the day, what it really just needs is the fact that the energy still goes like n squared. And whereas like the excited states on top of the ground state have order 1 energy, so that spacing is going to go to 0. That fact is still true, regardless of whether I'm in microcanonical or canonical. What's going to change now is the fact that the Hamiltonian has bounded fluctuations, means I can include it as an operator in the algebra once I subtract off the ground state energy. And that's going to change the structure of the algebra. Once I include the Hamiltonian, the structure of the algebra is going to change.
But finally, you are going to try to invoke the fact that the type 3 one algebra gets converted to some type 2 algebra, right? I mean, because type 3 algebras are pathological, right?
Yeah, so I'll get to that.
But I mean, to start with, if you did take the n equal to infinity limit, then that itself would have solved the problem of that being a type 3 algebra, right?
No, but the idea here is to try and understand the generalized entropy of the black hole. So if I don't take the n goes to infinity limit, I don't have some semi-classical bulk description. If I'm just at finite n, then we're just doing super Yang-Mills, and we don't really understand what the gravitational picture is in the bulk. So I have to work in some n goes to infinity limit in order to even get a black hole horizon that's smoothly defined in the bulk. I can't even talk about generalized entropy otherwise.
And this n is the n of the conformal field theory?
Yeah, that's right.
Yeah, so this n is, I mean, what is this n representative of? I mean, in the conformal field theory?
Well, in this case, it'd be like the n of the SUN. So the
SUN.
Yeah.
Okay.
Yeah. Okay, cool. So I want to make an identification between the boundary Hamiltonian, the one-sided Hamiltonian that we've been talking about so far, and some quantity in the bulk that's well defined in algebraic QFT. So in algebraic QFT, you never talk about one-sided quantities associated to some region, because as we talked about earlier, those things don't act smoothly on the bulk states. Two-sided quantities are fine, because, for example, whatever phase this on its own, whatever phase issue this on its own creates, the boost on the other side is going to work in the opposite direction and undo that singularity, that singular behavior created by the dephasing. So two-sided boosts are always well defined. And this quantity here, this modular operator, for our purposes now, is just the exponent. It's just e to the minus 8 psi, where 8 psi is this two-sided boost generator. The fact that this two-sided boost generator exponential is related to something like a modular operator is a very well-known result by Bisignano and Wickman. But the terminology there is not too important. Just think of it as the exponentiated boost generator. And it's, again, to emphasize, it's a two-sided boost generator, and it acts oppositely on the two sides. But what's important for us is we want to match the action of the Hamiltonian on the boundary to the action of some operator in the bulk that's also smoothly defined in the bulk. Now, the commutator of the Hamiltonian with any operator in the right algebra is just the time translation of that operator. And as we know, time translations in the bulk are related to boosts in the right wedge. In particular, beta times partial t is just the boost generator in the right wedge. So the two-sided boost operator, h psi, in the bulk has the same commutator as the one-sided Hamiltonian for operators in the right algebra. So what do I mean by that? I just mean beta times hr minus e naught is equal to h psi up to a term that commutes with everything in the right algebra. And I mean, in practice, x, this extra quantity here that I wrote down, x, that commutes with everything in the right algebra is just the left Hamiltonian. So all I'm saying here, I'm not saying anything fancy here. All I'm saying is the right Hamiltonian is equal to the two-sided boost generator plus the left Hamiltonian. And that's really just because the right Hamiltonian is really doing a one-sided boost, and the two-sided boost generator plus the left Hamiltonian is going to do a one-sided boost, because this is HR minus HL essentially, and this is HL, so the HLs will cancel out and you'll just get H right. But the reason I'm writing it this way is to make it clear that I don't, like this guy over here naturally does not have a decomposition into one operators because it's a type 3 algebra. So I can't write it as something that acts purely on the right minus something that acts purely on the left. You can only do that if you assume you're introducing some cutoff or something like that. This two-sided object, is as best as it gets in the bulk quantum field theory. But the point is there is this extra operator which commutes with everything in the right algebra such that the sum is equal to the one-sided boundary Hamiltonian. And you should think of this X as just being the left Hamiltonian. So this is an important point. So
I have thought it would have been beta times the left Hamiltonian.
Why? There's a beta. There's a beta there. Yeah, that's right. Yeah. Okay. Yeah. Okay. So we've identified this bulk operator, right? So X, some operator is going to come along for the ride for now, and it's some bulk operator which does the same thing that the boundary Hamiltonian does. So what I'm going to do now is I'm going to adjoin the action of X plus H psi to the bulk algebra associated to the right causal wedge, which is just the bulk dual of the algebra of single trace operators that we've been talking about so far. So what does that mean that I'm adjoining it? All that means is I'm going to take every operator in the QFT algebra of the right, and I'm going to hit it with e to the IS X plus H psi. Now that by itself, it seems like an uninteresting thing to do, but it actually leads to a very interesting structure called a cross product. So what is a cross product? So I'm going to take the algebra of, so the thing I'm going to do is I'm going to take the algebra of QFT operators, and I'm going to hit them with functions of X plus H psi. And this gives you something called a cross product because it's essentially an algebraic QFT version of a semi-direct product. What I mean by that is if you take any operator in the right algebra and you take its commutator with X plus H psi, that's going to give you something non-zero because this thing over here is just doing time like boosts of this right operator. But on the other hand, if I conjugate any operator in the right algebra by X plus H psi, the X part is going to go away because it commutes with AR, and I just have the H psi, and the boost generator generates what's called a modular automorphism. It takes the algebra into itself. So the action of this X plus H psi on any operator in the right algebra gives me back an element of that algebra. So it's really like an algebraic QFT version of a semi-direct product, but we call it a crossed product. So just to summarize, if I adjoin the X plus H psi, or think of it as adjoining the Hamiltonian to the QFT algebra, I get the structure of this crossed product. And for notational simplicity, I'm just going to write this as AR comma 0 cross product R psi, where R psi just means the group generated by X plus H psi. Okay. And so far, everything has been a bit abstract. I'm going to just mention one more thing and then explain physically what I'm actually doing here. So,
excuse me.
Yeah, of course. Yeah.
So, what is the difference between the cross product and semi-direct product?
There's no difference in terms of the structure. It's just that it's for an algebra, like as opposed to a group. That's that, but it behaves in the exact same way. It's just it's just the name is different. That's all. Yeah. Okay. Also, I don't know how I'm doing on time because I like still have like a few more things to say. Do you know how much time I have?
Yeah, no, we are pretty flexible with time. So
okay.
Take your time because there have been a lot of questions in between.
Okay, great. Thank you.
So how are the bulk operator algebra related with the boundary operator algebra?
Yeah. So if you ignore this cross product part that I did just now, then the claim is the algebra of single trace operators associated to the boundary theory that we talked about at the very start is dual to the algebra of the quantum field theory operators, the semi-classical quantum field theory operators in this wedge. So those two algebras contain the same operators in the holographic sense.
Yeah, but is there an explicit
yes, there is. I mean, I won't write it down, but it's this famous HKLL formula. So it's essentially just taking the Green's function for operators and just evolving them back like that, like just taking an operator here and using the Green's function to evolve them back to the boundary, and you get some boundary operator as a result. And it's going to be some integral of single trace operators.
No, I meant for your particular theory. Do you have a specific theory in mind on the boundary? Do you have a
I'm talking about, I'm specifically here, I have in mind n equals 4 super Yang mills, but it's just, it doesn't have to be so specific. You just have to give me some CFT which has a holographic dual.
Okay.
Yeah.
Standard HKLL reconstruction.
Yeah, that's right.
Sorry, maybe I should have asked this before.
Yeah.
So the one-sided boost was bad from the bulk point of view because it created a kink.
That's right.
And on the other hand, from the field theory point of view, it was bad because of the large N counting. So these two kinds of badnesses, how are they the same?
It's not obvious that they're the same, and I don't have a great answer to that question, because it is essentially the non-trivial thing about the fact that these two different badnesses exist is related to the fact that the horizon is emerging from the large N limit of the boundary theory. So mathematically they're not the same thing. It's just that the fact that there are these that the energy is not well defined on the boundary and the large N limit happens to give rise to this horizon-like structure, which has its own manifestation of the fact that you have a type 3-1 algebra. And the modular, so the modular Hamiltonian in the bulk is also has a continuous spectrum. That is the direct analog of the boundary description, the fact that the modular Hamiltonian has a continuous spectrum. The non-trivial part is that the theory in the bulk that has this continuous spectrum has a Rindler horizon-like structure. And when you have a Rindler horizon-like structure, then you have this issue with the non-smooth states. But that's sort of the special fact that a horizon is emerging, which is pretty non-trivial. I don't think there's like a very simple or direct intuition for that. At least I don't have any such thing.
Thank you.
Yeah.
Sorry, can I ask a question?
Yeah, of course.
I'm just getting slightly confused with this picture that Witten had in his cross product paper.
Yeah.
So the difference. So there in the large, strictly in the large N limit, the argument I thought was that HR, for example, does not exist in the algebra, and then because of the reasons you mentioned, that it's of order N, the energy itself blows up and the fluctuations blow up, so it's not in the algebra. So you take something that goes like HR divided by N, then you argue that that's central. Yeah. And then you say that if you go and in the large N limit, it commutes with all the operators. And then you say that if you're going away from the large N limit, the cross product was taking into account that operator, right? Was trying to accommodate that operator into the algebra. Right. But here it seems like you said something slightly different. You said the fluctuations of HR now are not blowing up in the large N limit because you did microcanonical ensemble. Yeah. And maybe related to that fact was that the operator that you're taking, which you are in the cross product, is not exactly the same as before. Is that right?
That's right. Yeah. So what? Yeah. Right. So what Witten considers in the other thing is this operator HR minus HR expectation value divided by N.
Right.
And you take a cross product with that. The reason I don't want to do that is for the reason I mentioned earlier, which is if you do it this way, then you have to do then everything is done in a power series in 1 over n squared. And then there are various quantities we eventually want to define, like the trace, which just won't be well defined. And you'd have to find a way to, accommodate for like algebraic QFT when your algebras are defined over some ring, in 1 over n squared, and it just becomes a whole mess. And we don't have control over that. So instead, you can just do microcanonical, where you can just work at n equals infinity. But the boundary Hamiltonian is not just classical gravity. It includes the quantum field theory fluctuations in it. It's essentially getting shoved into the microcanonical window.
I see.
Yeah. I don't know. Does that clarify the question? I'm not sure if that.
Yeah, I'm still slightly confused. Okay, so you're saying so part of the problem was that so you're saying one doesn't need to go away from the large end limit here. You'll still be working at n equal to infinity.
Yeah.
And the way you're doing it, since you don't have this problem that the fluctuations of HR are not well defined, you have already included those fluctuations at n equal to infinity.
That's right. Exactly. Yeah.
Right.
That's right.
Then why do you still need to do the cross product, for example? What else do you?
Yeah. So the point now is, so I think it's a little. In fact, if you do it in the 1 over n squared expansion, it obfuscates it a bit. The point is, you can, in this n goes to in this exact n equals infinity picture, you're just including the x plus h psi or the Hamiltonian in the algebra, the single trace algebra, but it has this structure. So in other words, I could have just written it as some algebra as a Hamiltonian, but it happens to have this additional structure where you can separate it into all the other stuff plus the Hamiltonian in this cross product form.
I see. Now I understand. So there the large n algebra was just what you're calling AR0, and then the finite n algebra was the cross product algebra. But here you're saying the large n algebra itself can be written as the cross product, and so
exactly.
I see.
Exactly.
Okay. Oh, cool. Thanks.
Yeah.
I mean, sorry to slow you down even further.
No worries.
I had the same sort of maybe type, which is what you've done is said, I'm going to work in this microcanonical state. HR is now well defined, and I'll include time development with respect to HR as well.
Yeah.
Just to make sure.
Okay. That's exactly right. And I in the next slide, I will spend a bit more time explaining a little bit more what you just said. Yeah.
Thank you.
Yeah. I just wanted to quickly first just mention the Hilbert space picture. And let me emphasize, when I say Hilbert space, I'm talking about the two-sided Hilbert space. I've been talking about one-sided algebras, like algebras associated to one side of the CFT or one side of the thermal field double or the other. But there's no way to define a one-sided Hilbert space. A type 3 algebra has no one-sided Hilbert space. There's a two-sided Hilbert space, which is what I'm really thinking of here. And so the Hilbert space of the quantum fields themselves is just given by, perturbations on top of the thermal field double. And so nothing special there. And let me emphasize that when I mean the Hilbert space of the matter, when I talk about this H naught, I'm including linearized gravitons in that. So the interesting physics here is not coming from linearized gravitons. Those are just some boring, for these purposes, those are just boring degrees of freedom that are thrown in with the matter. Okay. So that's the Hilbert space just of that's the Hilbert space associated to the single trace QFT algebra. You get it from the GNS construction, for example. If you do the GNS construction for this crossed product algebra, AR, where I've gotten rid of the comma 0, so AR without the 0, it means it's the cross product algebra. If you do GNS for that, what you get is the Hilbert space of the matter tensor producted with an extra Hilbert space, which is the Hilbert space of square integrable functions of this extra variable x, right? So essentially the left Hamiltonian, but for now, just think of it as a position variable x. And there's an associated conjugate momentum p to it. So our Hilbert space, again, is a Hilbert space of matter fields dressed with additional wave functions of x. So what is the physical picture for this Hilbert space? Like what is actually going on here? So what we're doing, as Sandeep just mentioned a few minutes ago, is we are taking the Hamiltonian. So if we're just doing this in gravity, what we're doing is normally we treat the ADM Hamiltonian as some classical object. What we're doing is treating it quantum mechanically and dressing all of our quantum states by a time variable, which we're actually treating as a quantum object. So remember that the conjugate to the ADM Hamiltonian is, so we normally think of the conjugate to the ADM Hamiltonian as actual time translations, but when we have a two-sided black hole, it's more appropriate to think of the conjugate to the ADM Hamiltonian as something called a boundary time shift. And the boundary time shift is just defined as follows. So I have some left time TL and a right time TR. I shoot a geodesic from the left to the right in a direction that's normal to the boundary, and it'll land on the right on some time T tilde. And this difference is a covariant way of measuring relative time differences between the left and the right. And the conjugate variable to the ADM Hamiltonian, the one-sided Hamiltonian, is really this time shift. And the reason for that is because of the gauge symmetry that says HL minus HR is equal to 0. So you really should be talking about this time shift instead. But the point is that the ADM Hamiltonian is conjugate to this time shift. And what we're doing is we're taking every quantum state and we're dressing it by this boundary time shift, except this boundary time shift itself can fluctuate. So it's really, you really think of it as an operator. So I have an ADM Hamiltonian operator, and then I have an associated boundary time shift operator, and I take all my quantum states and I have on top of them wave functions of this boundary time shift. So this is the sort of hydrodynamic mode that I had in mind. This is purely from the boundary, right? So, I mean, not from the boundary, but this is purely in terms of time. But you can think of it as a gravitational boundary mode. Classically, it's just a classical gravitational boundary mode, and we're quantizing that boundary mode. If you prefer, you can instead think of it in maybe a language that's more familiar, using the fact that the ADM Hamiltonian is equal to the area of the black hole. We know that the boundary time shift can equivalently be thought of as a boost angle. I don't want to use this picture in any precise sense because it starts getting into the murkiness of doing one-sided operations, but to have a picture in your head, this is completely fine. So boundary time shifts are going to be related to boosts, the boost angle in the bulk, this boost angle. If I have a slice like this, then as I drew earlier, you can have a slice like that, and that boost angle over there is some number, except now we're treating that boost angle quantum mechanically. And this boost angle is, you can think of it as a gravitational edge mode associated to the bifurcation surface. So the cross product Hilbert space is the matter Hilbert space plus this additional gravitational edge mode associated to the boosts. Sorry, so that was a lot of words, but this is an important part. So let me know if there was anything unclear, or if you have any questions about that.
So just so I understand, because, and you probably get to this because this seems really closely tied in the cosmological then setting to the problem of time, right? As in, that is, you're taking what was a classical variable on the boundary, just time.
Yeah. Yeah.
And promoting it now to a quantum variable. Is it?
Yeah. Yeah.
I see.
That's right. So in the cosmological context, we don't have a boundary time. Yeah. And so there's a Hamiltonian constraint in that case. And so what we instead in that case have to do is introduce the clock of like an observer as a quantum mechanical time to dress everything to. And then you have to incorporate the Hamiltonian constraint in order to construct the associated Hilbert space, which I don't have to worry about here, but yeah.
Yeah, I see. And just out of curiosity, you should go on. I mean, how big are the fluctuations of time in
So I will get to that. So actually I can just mention it now. So if you use the uncertainty principle, then so if the fluctuations in the energy in this case were order 1, so you can get the fluctuations in the time from that. Sorry, this is I think I'm missing some n.
Yeah, that's what I was asking.
I think it's 1 over n squared.
Okay.
I forgot the exact n counting here, but delta t I think is like 1 over n squared.
Okay, that makes me happy. It should be suppressed in n, right?
Yeah, exactly, yeah. Wait, let me just make sure I'm not messing this up. Sorry. Sorry, no, it's not. This is not right. I'm sorry. No, it is just order 1. I'm sorry. I was confusing the boost angle and the time. Delta t is order 1, and you're right. It should be suppressed, and I will get to that in a little bit. For right now, without any additional ingredients put in, the fluctuations in time are order 1, which does mean that you could be in like some superposition of many different boundary times, which is it's not very semi-classical, and you shouldn't like that. Later, what I'm going to do is introduce an additional parameter that by hand restricts me specifically to states where I'm not allowed to consider arbitrary superpositions in time. But that limits the kind of states you can consider, but you can't get around this. Yeah.
I see. Thank you.
Yeah. So,
sorry, yes. So I have perhaps slightly unrelated question. So in ADS 2 and ADS 3, you have this boundary gravitons, and this boost the operation is just one of the infinite modes of that algebra. So so I would so it's easy for me to understand this as some degrees of freedom associated with the boundary, but you were saying you can associate this with some gravitational edge mode at the bifurcation point.
Yeah.
And maybe this is speculative, but maybe this is what happens also in fluid gravity, where the fluctuations of the horizon can be transported along the null tubes. Fluctuations at the horizon. Maybe that's what's happening here.
No, I'm personally very sympathetic to that picture. Yeah, I think that sounds right to me. But I should mention though that in ADS 3 you're correct. There's all these there's an infinitely many symmetries, and that corresponds to infinitely many symmetries for the horizon as well. In the manner that you described, I'm pretty sure. And I don't have anything super concrete to say about those, but in 2D gravity, one important thing is if you actually construct the canonical Hilbert space after quotienting out by all the gauge constraints and everything, the only degrees of freedom in that Hilbert space are, in fact, the one-sided Hamiltonian and this boundary time shift, and there's nothing else. So all the extra Schwarzian degrees of freedom in the Lorentzian Hilbert space, they're kind of like they don't directly appear in the actual degrees of freedom that label the Hilbert space. So this is this construction by Harlow and Jafferis of the 2D Hilbert space of JT gravity. And that theory literally just has these boundary time shifts and the associated one-sided Hamiltonian.
Yeah. Okay, so these are the ones that are represented by the Schwarzian action.
Yeah, exactly, yeah.
So there, I wouldn't associate them with some gravitational edge mode
I think you can, because it's just, instead of talking about it at the boundary, you can just say, like, instead I'm talking about the boost angle at the horizon, and they're completely equivalent.
I see.
It's just, instead of boundary time translations, you just talk about boosts in the bulk. One of them is more well-defined, and if you're worried about that, that's totally legitimate. That, like, a one-sided boost, like we said, is not really well-defined. But at an intuitive level, whatever you do on the boundary, you can think of as doing something on the horizon if all you care about is talking about one-sided observables.
I see. Okay, thank you. Thank you.
Yeah.
Sorry, can I ask one question?
Yeah, for sure.
The way you define this algebra, even in the large end limit, it doesn't. So the right algebra doesn't seem to be commuting with the left algebra, right? Because you
mean the cross product algebra.
The cross product algebra.
That's right. It doesn't commute with the left. Yeah. So when you construct the left algebra, you have to be a bit more clever in how you write it down. Even at n equals infinity. Sorry, you don't have to do anything very different from what Witten did. But you're right. So the right algebra doesn't commute naively with the left algebra. So instead what you do is the commutant of the right cross product algebra is this thing here. Where now you take a cross product with just x instead of x plus h. This commutes everything on the right. But then, as you said, because the cross product has h in it, h psi, you have to basically strip that out of all the QFT operators in the left to get things which commute with the right cross product algebra.
Right. So okay, so the left algebra is okay. It looks like this where you have to put these.
Exactly. And so in that sense, this is actually something I wanted to emphasize later, but I'll emphasize it now. I'm using the terms right and left cross product algebra, but they're not literally associated to the right and left geometric regions, because they have a two-sided operator in them, which is this h psi. So it's not like they live in one algebra, one wedge or the other. They're sort of more abstractly right and left. And they're just some algebra and its commutant, basically.
Okay, thank you.
So yeah, for sure. So okay, so
psi is h psi is a Hamiltonian. Psi is a state in the psi is essentially a Thomofil double state, right?
Yes, that's right.
So that's essentially in the boundary. That's a boundary state, right?
So I'm freely switching back and forth between the boundary and the bulk. So the psi is the boundary thermofield double state, but it corresponds to the Hartle-Hawking state in the bulk. And so when I say h psi, I'm sort of being cavalier with the boundary versus bulk distinction, but I really mean the Hartle-Hawking state. But they're completely equivalent in as far as this particular discussion goes.
In that case, what would h psi be? I mean, if it is defined in terms of the Hartle-Hawking state?
It's this thing I drew earlier here. It's this two-sided boost. This thing here.
Okay. And another thing is, when you're talking about the map between the bulk operators and the boundary operators to the HKLL transformation, it actually means that the bulk operators are related to are non-local on the boundary, right? I mean, they're related locally to operators on the boundary.
That's right.
Is that taken care of? I mean, is it taken into account?
Yeah. Because they're smeared out in some interval in time, but you can squish them down to one time slice. But on that one time slice, it's just going to be some integral over a bunch of single trace operators, so it'll be in the algebra. So it's not a problem, in other words. Yeah, it is taken into account.
Oh.
Yeah. Okay, so just one last thing I want to say before I move on is even if there's no matter around, states with different boundary time shifts different boundary time shifts correspond to genuinely different states in this cross product Hilbert space. So even if I'm not doing anything to the matter and the state of the matter is just like frozen, if I change the boundary time shifts, this gives me different states in my Hilbert space because of the fact that these boundary time shifts are coming from these large diffeomorphisms at the boundary. So that's the sense in which I'm thinking of these as additional modes, or like gravitational edge modes or boundary modes, hydrodynamic modes, however you'd like to call them. They label the different time shifts, label different states in the theory, even if I'm not doing anything explicitly to the matter. And it's basically because the time shift is basically a dressing for the matter, and we're treating the dressing quantum mechanically. That's basically what's happening here. So all the interesting physics is going to come from this gravitational boundary mode. That's the part of the quantization that's relevant here. And in 2D gravity, this is the entire Hilbert space. This boundary time shift and the Hamiltonian associated to it is the entire Hilbert space. So you can imagine what we're doing is taking those two modes in J2 gravity. That same mode exists in higher dimensions, and we're just putting that on top of all the matter degrees of freedom. Okay.
One question.
Yeah.
So maybe you said this, but in flat space, are they analogous? Are they similar to the soft modes?
I am not including soft modes in this. I'm not 100% sure how the soft modes change the story. They will change it somehow. It's not immediately clear to me how. So in asymptotically flat space, I'm imagining I'm at spatial infinity. And so I'm just talking about the ADM Hamiltonian, and so just the boost also in flat space. But if you worked at null infinity, you would have these additional BMS generators.
Okay.
And it's not immediately clear to me what they do, although I can speculate on it maybe towards the end.
Thank you.
Okay. Okay, so why does any of this matter? So this is all a bunch of abstractions. So at a high level, I'm going to make a claim, and then I will hopefully be able to elucidate that claim explicitly. But the claim is, if you take a type 3-1 algebra, in particular a type 3-1 factor, and a factor just means the algebra has no center. So if you take a type 3-1 factor and you take its cross product with its own modular automorphism group, then there's a well-known result due to cons that the resulting algebra that you get is a type 2 infinity factor. Okay, so this is, again, just a bunch of words. So what does this mean? And so, by the way, recall what we're doing is exactly this. We're taking a type 3-1 factor, and we're taking its cross product with the right-sided Hamiltonian, or the bulk modular operator. And so we are taking a cross product with its own modular automorphism group. So for now, this is just a statement that I've said to you. It's not at all obvious why this should be true, but I'll hopefully be able to clarify that. So let me first explain what a type 2 algebra is. So a type 2 infinity algebra is one in which there is a trace, but the trace is not normalizable. So the trace, you can compute the trace for some elements of the algebra, but not other elements of the algebra. In particular, the identity element doesn't have a trace. But you can think of the trace of the identity gives you some infinite number, and you should interpret the type 2 infinity algebra as essentially a renormalized trace for everything else. So you strip off the infinite divergence from the trace of the identity from all the other traces, and you have a well-defined thing that's left over. So that's essentially what a type 2 infinity algebra is. I had this red comment here that a type 2 infinity algebra doesn't have an irreducible Hilbert space representation. Just don't worry about that. It's not too important. But the point is that these algebras there's no way to write down a one-sided Hilbert space for them. It has the same issue as type 3 in that sense. So the trace I'm talking about is a trace for the algebra. There's no associated one-sided Hilbert space that I can define. For that, you really need to go to type 1. But that's okay, because we'll be able to talk about entropies associated to one-sided algebras now that we have a trace. So it's not a problem, but it's something to keep in mind. Okay, so how does this work explicitly? How do we see that we have a type 2 algebra? So we take an operator in the right cross product algebra, which generically is so not generically, but a basis element of this algebra will look like this. So we have our operator from the original one-sided algebra AR, and we multiply that by e to the IS h psi, and then tensor product that with e to the IS x, right? So that's what a generic basis element of this algebra looks like. And then a generic operator will be some integral over S of this with some, some function, whatever, it doesn't matter. So I've been considering the thermal field double state this whole time. And there's an avatar of the thermal field double state in the cross product Hilbert space, right? So if I take the thermal field double and I take its inner, this thing here, sorry. Okay, okay, I'll just call it G for now, but I'll explain what it is. So I'm going to take the thermal field double state, and I'm going to tack onto it a state in the L2 of R Hilbert space in the cross product. In particular, I'm going to multiply it by the wave function that I use to define the microcanonical thermal field double. So this G here is really that f of E minus E naught thing that I defined earlier. I'm just writing it as G to keep things a bit more general, but you should really think of it as that F from earlier that I used to write down the microcanonical thermal field double. So this is a state in my cross product Hilbert space. Yeah, there was a question.
Yeah, so in general, shouldn't the psi and the x be entangled?
Yes, they should be entangled. I just didn't write it out explicitly, but yeah.
Okay.
Yeah, that's right. Okay. So I'm going to consider this particular state. So again, all I'm doing is I'm taking the microcanonical thermal field double and I'm essentially dressing it by a particular choice of a time shift. It's just a natural one that you would use to like foliate the eternal black hole. So an important thing that was shown by Witten, and which also follows directly in this microcanonical version, is the following statement, that I can take the modular operator of this psi hat state and split it into a quote unquote right part and a quote unquote left part. And again, here by right and left, I mean in this more abstract sense that I have an algebra associated to the cross product of the right, and I have its commutant. They aren't literally living in the right and left wedge for the reasons I mentioned earlier. So what is this modular operator here? It's no longer, the exponential of some boost generator or something like that. You're going to have to use the actual abstract definition of the modular operator, which we don't need to get into the weeds of. For our purposes, the modular operator for some state, in particular the state psi hat, but this definition is true for all states, is just given by this. So the modular operator is completely fixed by this particular condition that expectation values with two operators B and A just flips them around. So you take this condition here, and you can show that this modular operator can be split into two pieces where delta R lives purely in the right cross product algebra and delta L lives purely in the commutant. So we say that now the modular operator generates an inner automorphism because it can be split into pieces associated to the respective algebras. This is really nice because we weren't able to do that before. In a type 3 algebra, there's no way to split the modular operator of your generating state into a left and a right part. But now for this cross product, we're able to do that. And the way you do, and the explicit expressions for delta R and delta L are given here. And it doesn't matter too much what the expressions are, but what I want to emphasize is the way we're able to do this split is crucially because of the fact that we have this cross product. Because if you notice, delta R here has the modular operator of the QFT in it. So I'm not splitting anything with the QFT modular operator. if you look at the modular operator associated to the left algebra, it's purely just a function of x. It doesn't depend in any way on the matter sector of the left. So the splitting is really coming from the fact that I have this extra L2 of R piece. It's not obvious to see why this multiplied together satisfies this thing, but you can just take my word for it. It's a simple computation that you can do and check. But the point is that I can split it into a pure function of x in the left and the modular operator of the original QFT plus this extra piece associated to the cross product of the right, the x plus h side. Because we can do this, this cross product algebra cannot possibly be type 3. Because as I said, in type 3, you can't split things this way. So it has to be a type 2 algebra. And
sorry,
yeah.
If you go up slightly on that, the thing you've written in green on the right, are you missing a delta psi on the left hand side in that equation?
No. Yeah, there is no delta psi on the left hand side here. You mean here?
Yeah.
Yeah, no. So the delta psi hat is defined by, well, it's not defined, but it's given by the fact that if I take delta psi hat and I sandwich it with b hat and a hat, then
it just literally becomes
it just literally becomes AB. And so, I mean, the actual definition of the modular operator is first you start with this thing called the Tomita operator.
Right.
Which just does this. I'll just remove the hats for now. I did the same thing with the hats, just easier to write. And so, and the modular operator is given by S dagger S. So if you take this definition, you notice here that S acting on the A gives you back something that's just A dagger. And so if you just take S dagger S and stick it in here, essentially all it does is it'll dagger the A and the B, and then you can use the fact that it's daggered to switch the two.
Okay, thanks.
Yeah. It's just this version is easier because then you can extract the formula for delta psi.
I have a question. In this formula, you still can't define it to be something like a trace, because a trace would have to have trace AB equals trace BA. You still have
I haven't gotten to the trace yet, and I'll explain that. Yeah. I'll be able to write down a trace, but I will get to that. Yeah. And it'll answer your question about the trace AB equals trace BA.
Okay.
Yeah. Okay. So one more thing I want to note is there's a symmetry associated to this x variable in the definition of the cross product, which is just I can just shift x by any constant and it's not going to change anything because x plus h psi and x plus h psi plus a constant generate the same group. So what that means is there's a freedom in how I define this delta R and delta L in this decomposition here. I can multiply delta R by e to the minus c. I can multiply delta L by e to the c, and it's not going to change anything. So that overall rescaling symmetry is relevant because it's essentially the reason you get a type 2 infinity. The trace will only be defined up to an overall normalization, and therefore the entropy will only be defined up to an overall constant. So you don't get an entropy, you really get entropy differences, but I will get to that. So the trace can now be defined as follows. So the trace of any operator in the cross product algebra is just given by taking delta R inverse, multiplying that by the operator of interest and taking its expectation value in the state psi hat. And you can check that if you have, say, a type 1 algebra, this definition of trace will agree with the usual definition of trace on the actual Hilbert space of states. But here we don't have a Hilbert space, and this is the next best thing, abstraction that we have. And you can check that, I mean, I won't show it to you here, but you can check that this definition satisfies, in fact, this is how you show that it's a trace. You show that it satisfies the defining property of the trace, that trace AB equals trace BA. This particular definition will satisfy that. And that's actually how you write down this formula.
I have a question.
Yeah.
Like usually in the definition of a trace, you sum over the ket and the bra, right? I mean, you sum over the states which you're taking the expectation values. So here, why aren't you doing that?
So so it's a little bit different because I don't have a Hilbert space. You can't really think of it as in a literal sense as a sum over, for example, eigenvalues associated to some particular basis decomposition. So here, this expectation value here doesn't mean that I'm like just considering one particular matrix element in the analogous quantum mechanical formula. It's just that whenever you write down formulas in algebraic QFT, you typically can convert them into expectation value type formulas starting from the base state that generates the algebra. But if you were to write this out in ordinary quantum mechanical language in a type 1 algebra, it would turn into a sum over energy eigenvalues. It's essentially coming from the fact that this guy here contains the spectrum in it. So the fact that I'm taking the expectation value here, don't let that fool you into thinking it's like some one specific matrix element. I really am summing over all the different elements of the spectrum. If I do a spectral decomposition of this thing here, that will become evident. Yeah. Okay, so as I mentioned earlier, because this delta R is only defined up to an overall rescaling, the trace is also only defined up to an overall rescaling. And this is a defining property of a type 2 algebra. So far, I've gotten down to the point that I've shown that we have a type 2 algebra. And you can write down a formula for this trace just by using the definition of the modular, not the definition, the expression for the modular operator I wrote earlier. You can derive a simple formula for the trace, and that formula is in this boxed thing here. And in particular, if you'll note, so in general, this a hat here is a function of x. If I consider operators that are independent of x, then this trace is just going to blow up because it'll just end up being an integral dx e to the x. If I consider operators that are smooth functions of x that decay sufficiently quickly, then this trace will be well defined. So in particular, the trace of the identity is going to be infinite. And so that's the sense in which this is a type 2 infinity algebra. And you can think of that, like I said, the trace of the identity is just some infinite renormalization. The fact that I can rescale the trace by any overall constant, you should think of that as saying I can just strip out the trace of the identity and have some trace that's left over that makes sense for all the operators that smoothly depend on x.
Question?
Yeah.
So as far as I remember from Witten's paper, his definition of this trace in terms of this matrix element was invoked by saying that when you can express it in terms of a density matrix psi A, where psi ket psi bra, trace rho A, where rho is ket psi bra psi. Isn't that correct?
Yes. That's correct. Yeah. So that, yeah.
And from there he said that since psi is a mixed state, it essentially gives you the identity. I mean, it's a maximally mixed state, so it essentially reduces the density matrix reduces to the identity matrix, and so that is why you get the trace. Isn't that correct?
No, I don't think that's right. I mean, in general, it's not going to be maximally mixed. I mean, the density operator could have many different like entanglement propries.
If it's not maximally mixed, then it wouldn't lead to the trace because you have to have the trace of rho psi to be the rho psi has to be the identity in order to give you the trace, right?
Maybe I'm not following. So here I don't need a density operator to define a trace, right? Like I can use the trace to define a density operator, but you first define a trace and then you can talk about a density matrix, but you don't use a density matrix to define a trace. Like I don't have a way of defining a density matrix without having a notion of trace in the first place. So here, yeah.
Here the thing is that since, I mean, as you said that taking a certain state and not summing over all possible states is, I mean, what you're saying is that that is tantamount to that psi being a mixed state.
I'm sorry. I think I understand what you're saying. Yeah, the rho psi hat. You're talking about rho psi hat?
Yeah.
Rho psi hat does have the structure of because it's the cyclic and separating state generating a type 2 algebra. It's going to look like a maximally mixed state. That's right.
Yeah.
That's right.
Yeah.
Yes. Sorry. Yeah, I see what you're talking about. Yeah.
Okay.
Yeah, that's right. Like rho psi will look like a thermal field double type state, and then rho psi hat will look like a maximally mixed state. That's correct. And all excitations on top of it will almost look like maximally mixed state.
Yeah.
Yeah, that's right. Okay. Last thing before I try to convince you generalized entropy is the entropy, and then I won't bore you any further.
Sorry, Ven, very sorry to slow you down, but
no.
Just so I've not lost complete track of what you're saying. This A hat of X, the parameter X is what you obtained in the cross product, right?
I'm so sorry, I overloaded the notation here, but it's just A of X, but yeah.
Yeah, okay. The X dependence is what you got when you did your translation but to go into the cross product, right?
That's exactly, yeah.
Okay, good, thank you.
Exactly. And you can think of this as saying I'm dressing these operators by some time variable.
Yeah, and then you're integrating over that time variable. It's like a time average of sorts.
Because it's in general, there's some weight function of X. So when I compute a trace, I also have to integrate over X.
Yeah, it's very.
That's right.
I see.
And so in particular, the operators that you have before you did the cross product, for those operators, this trace is not well defined.
Exactly,
right?
Because that's right. There's no dependence on X, and it's just and it's going to blow up, for everything. But now it won't blow up for some things.
For some things which necessarily needs to include the factor that came in the cross product.
Exactly.
Right. Okay, thanks.
Hi, may I ask a question?
Yeah, of course, yeah.
Yeah, so actually, you have here a very specific, of course, system in mind, the TFT state.
Yeah.
But I mean, more maybe generically or algebraically. So when I am given some state psi hat, then just like you just said that delta psi hat is schematically like delta R times delta L. And this R is basically, I can think of it as, made up of H psi minus, this X, or which I should think of as HL, and then the rest is by HL or X.
Yes.
So, I mean, how, so more generically, not for this case, but more generically, how unique is this? I can have any X, right, which I...
Absolutely. Yeah.
So,
So you can have any X is fixed up to an overall constant, but
even not constant. I mean, I can subtract out any X from, probably, always not have a geometric description of that, but I can always take out something from H psi and add it later on.
That's right. So it's not, in that sense, it's not, you're right. The fact that it's X plus H psi, like in between those two, you can always shift around X in any way you want, as long as it doesn't change the fact that it commutes with the other side.
Right.
It's fine. You can do lots of things, right, that don't commute with the other side. So in a generic, in a generic quantum field theory, there are many different X's you could write down if you wanted to do this type 2 algebra construction that would all give you a type 2 algebra. And there's no canonical way to fix what that X is. The only advantage here is because we have, because we're doing this specific thing with the eternal black hole, there's a way to geometrically fix what X is supposed to be.
Indeed,
The reason you care about that is that eventually then you could connect it to the generalized entropy. Otherwise, you can just pick whatever X you want if all you care about is getting a type 2 algebra.
Yeah, I understand. So, but shouldn't I be then worried about, so when, in Wheaton's review, he talks about this Tomita operator. He's talking about some unique decomposition in terms of J and delta of this Tomita operator. And this, you just used some property of S to, show some trace relations, which kind of relied on the fact that S had this unique decomposition. But if this uniqueness is lost, should I be worried that I can have any delta and because delta can be
so
once of any delta and delta L, maybe there is a problem with this Tomita construction.
So the claim is once you fix an algebra for me, then the decomposition of the Tomita operator
is unique. Okay, so that's the
so here it's just you can worry about why you fixed this particular algebra, not some other one with some other choice of X, and that's a valid thing you could bring up. My claim is just this is the choice which naturally comes from ADS-CFT or from gravity. You can forget ADS-CFT. It's just naturally what comes from gravity. If you were in an arbitrary QFT trying to do this, there's no easy way to like specify what X is. So actually, basically, maybe this is a very highbrow way of saying that if you're doing semiclassical gravity, gravity is naturally telling you how to like mix together area and matter entropy, and you shouldn't try to separate them. But in an arbitrary quantum field theory, there's no natural way to regularize the entanglement entropy. In gravity, there is, and it's just the area term, and that's essentially what's coming out of this formalism. But yeah.
Hi, Ven. Sorry to interrupt. We are almost about at 2-hour mark. How much more time will you need?
I think I can get through it in 10 to 15 minutes if that's okay.
Yeah, so let's postpone all the questions to the end and let Ven complete. Sorry.
Yeah, no worries. Okay, so sorry. One last thing. So now that I have a trace, I can define density matrices, right? So if you give me some state psi hat in this crossed product Hilbert space, where again psi hat is some excited state of the matter plus some arbitrary wave function of my time coordinate. It's not necessarily the thermal field double. It could be some matter floating around on top of the thermal field double, and it's also not necessarily the time slicing I use for the thermal field double, this f function f window function I defined earlier. The wave function of x that's used in this could be some arbitrary thing. So it's an excited state both in the matter sense and in the sense of the extra L2 of R part. Okay, so you give me some state like that, and I claim I can define now an associated density matrix for it. That is, it should not be equals to, just means it's an element of. So there's a density operator in this cross product algebra, and you define it by the statement that the trace of this density operator times any operator A gives the expectation value of that operator in the state phi hat, this excited state. And since the trace is only defined up to an overall constant, I need to also give the density operator this rescaling freedom in order to preserve the normalization of the density operator. And so as a result, the entropy, the von Neumann entropy itself is defined only up to an additive constant. But what's nice is now I can actually define von Neumann entropies. I can define them up to an overall constant, but that's way better than what we had before, where we couldn't define them at all. So now I can just write down trace rho log rho, and I can try and compute it. And there's some words I want to say about this, a little more intuition for what's going on, but I'll save that for the end maybe. And first, I'm going to quickly try and convince you why this formula that I wrote down for the entropy, this trace rho log rho formula, is going to be related to the generalized entropy. So recall that the setup we were considering is this perturbed black hole. I have some internal black hole and I have some stuff falling in. And let V label the affine parameter along the event horizon. So the two surfaces of interest are going to be the bifurcation surface and the surface at infinity. Okay. And this point that was brought up a while ago about the fluctuation in the time, I'm going to just quickly go back to that. So we want to restrict ourselves to so-called semiclassical states. So states in which the fluctuation in the boundary time shift is small, because we don't want to consider states where we're considering superposition of geometries with vastly different time shift. It's not a very semi-classical situation. So I'm going to restrict myself to cases where the fluctuation in the conjugate momentum is order epsilon, where epsilon is some small number that I'm tuning by hand. It's independent of n, it's just some small number. So I'm by hand restricting myself to these semi-classical states. So there are lots of states in this cross-product Hilbert space that we won't consider if we do this restriction, but these are the ones that we really care about. So we take n to infinity first, and then we take epsilon small. And so this an example of a semi-classical state, or a general form of semi-classical state, will look something like this. So you give me some matter state. You give me some matter state phi, and then I'm going to take a superposition with some state of x that's convolved with some wave function g of x. And again, this g here can be any arbitrary g. It doesn't have to be the wave function you used for the microcanonical thermal field double. It could be some other distribution over the boundary time shifts. So my claim is that there's a formula you can write down for the von Neumann entropy of such a state. And this formula just comes from taking the definition of the von Neumann entropy in the cross-product Hilbert space, the cross-product algebra rather, trace of rho log rho, and just manipulating it into this form. So it's nothing fancy. I'm not going to show it to you because it's technical and it's not really insightful in any way. What's important are the individual elements that show up. And I'm going to try to convince you that they're related to the generalized entropy. So there are three terms in particular that show up in this formula for the entropy. There's the expectation value of x plus h psi in the state phi hat. There's the expectation value of this thing called the relative modular operator in the state phi hat. So the relative modular operator, just really quickly, is just defined as the thing which does this. You take some operator, it acts on phi, and it spits back out the same operator conjugated acting on psi. And h, and then I'm just defining h of psi with respect to phi as the thing which is minus the log of the modular operator. That's all. So this quantity here, in algebraic quantum field theory, is the same thing as the relative entropy between phi and psi. So really what I have here is expectation value of the energy of the right boundary. Remember, x plus h psi is beta times the energy difference. So this is the energy difference between the thermal field double and the excited state. This is the relative entropy. And this term here is going to come along for the ride, but it's essentially the entropy of fluctuations in the energy. Okay, so what is the interpretation of these terms in terms of actual gravitational language? So for now, I'm going to ignore the fact that we really have a type 3-1 algebra for the bulk quantum field theory in order to make contact with quantities that we're normally used to thinking of when we introduce a cutoff. So to start with, we have this relative entropy that showed up, right? Now, a standard fact about the relative entropy is you can always decompose it into two pieces. You can decompose it into the expectation value of the one-sided modular, this is the one-sided modular Hamiltonian. So you can decompose it into the expectation value of the one-sided modular Hamiltonian in the state phi, minus the difference in the entanglement entropies between the states phi and psi. And again, these are all regular entanglement entropies associated to the quantum field theory. So I'm ignoring type 3.1 issues here. Secretly, these can't be defined, but this is just to tell you what's going on. Okay, so relative entropy is expectation value of the modular Hamiltonian. So this thing is just the boost energy of my excited state. And on the other hand, expectation value of x plus h psi is just, like I said, the difference in the energy between the excited state phi and the thermal field double state, which is the same thing as the difference in the area of the excited state and the thermal field double state. And that's because the energy of the right boundary is equal to the energy, it's the same no matter what slice I consider on the boundary, so I can push it all the way to future infinity. And at future infinity, there's no matter falling in. So the energy at infinity is just equal to the area of the black hole at t equals infinity. So expectation value of x plus h psi is just the area at future infinity minus the area of the original bifurcation surface. But I can use Ray-Chaudhuri's equation to relate this difference in the area to the modular Hamiltonian that we had earlier. The way you do that is you just take Ray-Chaudhuri's equation in the linearized approximation. You ignore terms that are second order in G Newton. You integrate it 2 times. And you'll find that the area of the bifurcation surface in the state phi hat, so not, so it's not in the state psi hat, right? The area in the state phi hat is equal to the area at infinity in the state phi hat plus the one-sided boost. So what that means is I can rewrite expectation value of x plus h psi as the area of the excited state at the bifurcation surface minus the area of the thermal field double state at the bifurcation surface plus the boost energy. So all I've done here is I've plugged in this formula in to this expression here. I've solved for the area at infinity in phi hat in terms of the area at the bifurcation surface in terms of phi hat and the boost energy. So all in all, if I plug all that in, here's the formula that I get over here. I find that the von Neumann entropy of the cross product Hilbert space is equal to the area in the excited state of the bulk at the bifurcation surface plus the von Neumann entropy of the excited state plus this correction to the area term coming from energy fluctuations. This was something that's computed a long time ago in this paper, for example. And then I have this state independent constant, which essentially just subtracts out the area of the bifurcation surface in the thermal field double state minus the entropy of the Hartle-Hawking state, the one side, the reduced density matrix on one side of the Hartle-Hawking state. So it's a completely state independent constant. No matter what excited state I consider, this is the same constant that's going to show up. So an important point here is that this area term here differs from the area of the thermal field double at order G Newton, even if no matter is around. Even if I didn't excite the black hole, and all I did was consider different boundary time shifts, these areas will differ because different boundary time shifts correspond to different wave functions of energy. And those different wave functions of energy are going to differ at order 1 from one another. And in the bulk, that corresponds to order G Newton differences in the area. So even if like I got rid of all the matter, the area here differs from the area here at order G Newton. So this is genuinely giving me the contribution to the entropy from the gravitational boundary modes, or these hydrodynamic modes. And if you stare at this formula here, it's just a generalized entropy up to this overall constant. So what we've shown is that the von Neumann entropy of this cross product Hilbert space gives me the generalized entropy of the black hole plus this state independent constant. So we've been able, we're able to now recover variations in the generalized entropy as coming from an actual trace over an algebra. And since we're dealing with the type 2 infinity algebra, this is the best we can do. It's only going to be defined up to some state independent constant. But it's really nice, even though it's giving you variations in the entropy, it's still very nice because it gives you a single density matrix from which both the area term and the matter entropy term come out of the same mechanism. You're just giving me some density operator where there's a gravitational boundary mode dressing your matter fields. You take some trace rho log rho, and both the area term and the matter entropy term pop out up to this overall constant. It's not treating the two in a different way, and it's telling you that in this effective quantum gravity Hilbert space, the area term is really just coming from the gravitational boundary mode associated to time translations or boosts or however you want to think of it. And so this is the sense in which there's like a Lorentzian picture for the generalized entropy as an actual von Neumann entropy. Okay, so I've been going on for monologuing for quite a while, but that's the main result. So I'll end it there, and then I can always explain some like comments on what more there is to say, but let me just end it there for now.
Thanks. Let's thank Van for the wonderful talk.
Sorry, and why this entropy proportional to the area, not to some function of area?
Why is it not a function?
Why just area itself, not some area square or area or logarithm area or something like?
I mean, that's just what pops out. You get the area because the entropy is given by the expectation value of energy differences, and energy differences directly correspond to area differences for the black hole. Yeah.
Due to the Raychaudhuri equation.
Yeah, through Raychaudhuri. Yeah. Yeah.
Okay. Thank you.
Thanks for a great talk. I'm sorry I have to run, but
no worries.
I'm curious to hear about your comments regarding deSitter space. So perhaps we can have you back, because also at least my brain is kind of fried after 2 hours. So So maybe we can have you back in one of our journal clubs to expound on the deSitter angle. Would that be possible?
Absolutely, yeah. Whenever, I mean, I can do it whenever. So whenever you guys would like, I can tell you something about deSitter.
Okay, excellent. I'm going to run off, but thanks a lot for a great talk.
Thank you so much. No, that was really fun. Thank you.
Can I ask a question? Yeah,
please.
So you're using this formalism. Can we also comment on generalized second law? Like,
that's a very good question. And the annoying thing is, so there's the most naive thing you would hope to do is take the setup. And so everything I told you about right now is for the entropy of the bifurcation surface, right? But if you consider some other cut of the black hole horizon like that, you might hope to say something about this wedge over here.
Right.
And then, so if you can say you were able to associate a cross product algebra to this wedge, and then you get some generalized entropy associated to a von Neumann entropy of that wedge, then you can get the GSL from some nesting of algebras and inclusion property of the trace in the von Neumann entropy. But the problem is, this is not actually a well-defined algebra. And the reason for that is if you want to do the cross-product construction, you need to include the Hamiltonian in the algebra, right? But since the Hamiltonian is exactly well-defined at n equals infinity, I can take any operator in here, evolve it by the Hamiltonian for as long as I want, and just move it out of this region.
I see.
So you won't get a closed algebra.
Right.
So that prevents you from in a very straightforward way getting something like the GSL, because there's no easy way to associate an algebra to other regions. The bifurcation surface seems to be very special in that sense. There's probably some more clever way to do it, but we, at least as of now, we aren't aware of such a thing. So instead, in our paper, we talk about other scenarios where you can get a GSL that isn't this like continuous GSL where you're deforming up the horizon. You see that generalized entropy is increasing. But you consider situations like you take a black hole, you throw shocks at the black hole, you allow the black hole to perturb, scramble, settle back down, and you compare the algebra of the settled down black hole to the older one, and you show that there's a GSL coming from some nesting property of the algebras. So we can show things like that, but it's like a discrete GSL, if you'd like.
Maybe one more very naive question. So in all those papers by Hong Liu and Witten himself, so you have been referring to the Bizonano-Wichmann theorem and the Arakis theorem for type 3-1 results, right?
Yeah.
But those, if I'm not mistaken, those theorems, an input in those theorems is the Lorentz symmetry, right? So why should we expect those results to carry over to a curved spacetime result, QFT in curved spacetime?
So for a generic curve background, it's not going to work, but you can show that it generalizes very straightforwardly to any situation where you have a killing horizon. So the fact that it's Rindler is not particularly special.
I see.
If you have any killing horizon, the Bisognano-Wichmann theorem will work.
And for the Arakis result, like so the algebra of local region is type 3-1. That's a
that one will also work. Yeah, that one will also work for a situation where you have a killing horizon. So a something like an eternal black hole. You can derive. You can show that Araki's result and Bisognano-Wichmann and all those things still go through. The analytic structure of the modular flowed correlation functions is essentially the same, as long as you're just talking about the exteriors and you're not trying to say anything fancy about the interior of the black hole.
Can you suggest a reference where this has been like explicitly shown, or I will like just concluding based on the model flow structure that they are very similar?
Off the top of my head, I don't know of a rigorous reference that shows it. I'm sure there is. I just don't know off the top of my head. But if you look at Edward had a recent like review article called something about quantum field theory and curved spacetime, like why thermodynamics makes sense or something. And in that, he definitely talks about, like, he gives some reference that talks about Bisognano-Wichmann for killing horizons. Yeah.
And maybe if we have time, one more question. So that X that you wrote, that is beta HL. Could I like so that X has to obey the condition that it commutes with every operator in the right algebra.
Yeah.
So could I as well add a constant that is n dependent?
You can't. Well, so we're working. So everything here is at n equals infinity. So there is no n dependence left. Everything is exactly at n equals infinity. You could ask if you were doing things instead in the perturbative in 1 over n expansion, like what would happen in that case? That constant could depend on n, and that would probably like complicate matters quite a bit. But in this version, it can't.
Okay. Thanks a lot.
Yeah, of course.
Can't you show once more how you have got the relation between entropy and area? There was formula which you obtained without yeah. So how in this formula area appeared?
Yeah. So the way the area appears is the entropy formula has this expectation value of x plus h in it. X plus h, if you remember, is just the right Hamiltonian minus the energy of the eternal black hole or the thermal field double. So x plus h psi expectation value in the state phi hat is just the energy of the right in the state phi minus the energy of the black hole, minus the energy of the eternal black hole. So it's the energy of the perturbed black hole minus the energy of the eternal black hole. And the energy of the perturbed black hole is equal to the area of the black hole at future infinity, because the energy of the right boundary is conserved. So if I take the energy on any slice, I can just push it up to here and it's going to be the same energy. But the energy over here is just equal to the area of the black hole here, because by then all the matter has fallen in and there's no matter energy left. So the energy of the right boundary in the excited state phi is equal to the area of the black hole at t equals infinity after the black hole has settled down. And the energy of the eternal black hole is, of course, just equal to the area of the bifurcation surface, because there's no matter in the first place. It's in the Hartle-Hawking state. So that's how you go from energy difference to area difference.
And coefficient 4G you obtained from Hawking, or you?
No, this 4G comes from like the first law, which says that the energy is equal to the area divided by 4G. It's like the surface gravity, basically.
Thank you.
Yeah.
One thing whether. Oh, go ahead.
Sorry. Yeah. Thanks, Vel, for that nice talk. Just wanted to ask you, so in the earlier Witten's picture, the large n algebra was type 3, in 1 over n it became type 2, and then the expectation was that if finite n it becomes type 1, right?
Yeah.
So how does that work here now? In the large n it's already type 2, and then what happens if you, what do 1 over n corrections look like in this, or finite n?
So here perturbative in 1 over n corrections won't do anything interesting. But finite n expectation is that it's still a type 1 algebra. That story won't change. Yeah.
That has to be the same. And then you're saying corrections in 1 by n doesn't do anything.
Yeah.
Okay.
It'll just change the fluctuations by some perturbative amount. Like it won't do anything interesting.
And maybe if you come back and talk to us about the DS case, maybe I can ask you. That would be nice. I can ask you this then. But let me just ask it anyway and see if you have a any small comments to say about the asymptotically flat case, where let's say we have some black hole formed by collapse or something, a one-sided black hole. Then how much of this story do you think?
Yeah. No, that's a great question. So the case of an asymptotically flat space, the case that goes through almost identically is the eternal black hole again, but an asymptotically flat space. Then everything, the story is pretty much the exact same thing. Just don't use CFTs anymore and just use the ADM Hamiltonian everywhere. For the collapsed black hole, the story is more complicated. And in that case, you can't, you can still talk about generalized entropy, but it's a bit more tricky. You can't just go through this whole formalism of taking a cross product by some boost generator and getting some nice generalized entropy that's just a trace of like trace of rho log rho. At least we're not aware of a way to do that. But what you can do in the case of a one-sided black hole is talk about, so you can consider an algebra at some instant of time on some time slice that cuts through the interior, for example, and then an algebra associated to a later time slice. And you can ask about the differences in the entropies between those two algebras in the limit that the later time slice goes to future infinity, so that it settles down to an actual like stationary black hole. So you can talk about the generalized second law still by essentially considering the original time slice to a time slice that's really far in the future, so that it essentially looks like an eternal black hole, and just saying that showing that the algebra at the very end has to be larger than the algebra you started with. But it's hard to like say something more fine-grained about that entropy using this formalism, at least as of now.
I see.
So in other words, you can argue the algebras are increasing in size, and therefore any entropy you can associate to it has to be increasing. Sorry, algebras are decreasing in size. Decreasing in size. And so the entropy has to be increasing, but you can't really but it's hard to write down a formula for that entropy.
Got you.
Yeah.
Okay.
It's a great talk. I really loved it, and I have already asked 1 million questions. So let me make it 1 million plus 1.
Okay.
So in case of JT gravity, so I'm still struggling with why the the boundary graviton mode, the large diffeomorphism can be equivalently be thought of as living on the boundary or at the bifurcation surface. So the following thought comes to my mind, that in case of JT gravity, one-sided black hole, you can think of an end of the world particle deep in the interior, and the boundary particle, if you wish, or at the boundary. And now normally we think of the Schwarzian mode as describing the boundary particle, of course. But there is an SL2 or gauge symmetry which ties the motion of the end of the world particle with the boundary particle. So is it some such thing that allows you to ascribe the the Schwarzian kind of mode to? Is it like the thing of the world particle?
Absolutely. Yes. I think the thing that maybe was making you not like the words that I said, for a valid reason, is I kept drawing this picture where I have like a two-sided black hole. But really, when I say that you can think of the boundary timeshift as a gravitational edge mode at the horizon, what I'm really imagining is you're treating the horizon as an actual internal boundary. And so you have to introduce some cutoff brane of some kind, or an end of the world brane or whatever, like that hugs the horizon. And so you just, so then you have to like just delete the rest of the space-time. And then the claim is that whatever the boundary timeshift does, because of the bulk Hamiltonian constraint, that's the same thing as fluctuations along this, like in the boost direction along this cutoff. So it's just saying that I have some end of the world brane that I'm treating dynamically in terms of its in terms of the boost angle that I use to relate this cutoff surface to the boundary like that. Like there are different ways to relate the boundary time to this thing via this boost angle. So yeah, there is some like wall that I have to put inside.
I see. Okay. Thank you. Thanks a lot. Great talk.
Thank you. Yeah.
Okay.
I was just wondering whether this X, instead of the X operator that you have, whether you could kind of incorporate more operators in a sort of and treat it as a many-body theory, and kind of generate the sort of shock waves that are needed in order to give the GSL. This is a vague speculation, but I don't know.
So one thing is that these X's have to essentially be, in order for this to work, they essentially have to be conserved charges, and the conserved charges that are relevant are the non-compact ones. Like if you try to do this cross product with, say, angular momentum or something, you're not going to get anything interesting. But because the boost is non-compact, it ends up giving you something that's interesting. So it limits the kinds of X's you can consider in order to like get this generalized entropy out. If you consider multiple shocks, you're right that there are different X's that come from all the different, like each shock corresponds to some particular algebra. So later and later algebras in time that you send out shocks from, each have their own X's. So there's a whole family of X's that you have for all the different shocks you use to enlarge the black hole. And that ends up being related in an interesting way to out of time ordered correlators and things like that. So this is something we talk about at like the later sections of our paper.
Okay.
So I think there is something to the effect that you were describing, if I understood it correctly.
Yeah, exactly what I was saying. And another thing is that whether instead of considering SUN gauge theories, maybe you can consider random matrix theories of, in the double scaling limit, which have also infinite n, and consider the analogous situation, right? I mean, you don't have to restrict yourself to gauge theories with SUN gauge group with n equals infinity, because random matrix theories are essentially defined in, they can be, the n is actually the n of the Hilbert space of the boundary theory.
Yeah. No, there's definitely an analogous kind of thing that seems to happen in. So this is probably Yeah, there's probably an analogous story for random matrix theory. Something that's in between random matrix theory and what I described is, for example, SYK.
Yeah.
And there seems to be an analogous story in SYK where you consider a certain sub algebras of operators in double scaled SYK, and in that limit you get something that looks like a type 2 algebra composed of like matter operators and like the length operator of these chord diagrams in the bulk.
Yeah.
So some interesting thing like that. So I would be hopeful that there's an even more general story for random matrix theory, but I don't have anything very useful to say. But I share that sentiment.
Okay, so after a lot of questions, let's thank Ven for a wonderful talk. Thank you much.
Thanks, Ven.
Thanks, Ven. So we'll maybe contact you for the deSitter part. So
that's good.
Thanks a lot.
Thank you. Have a good day.